Okay, so let's come back to lecture number 3 in network security. So the last time we finished the overview on networks in general and started with cryptography. Especially we looked into the elements of symmetric encryption and learned that we have basically 3 kind of elements that we apply in various orders. So the first element was to have some kind of permutation on the input, so we just reorder the positions of the bits. That allows us to based of course on the key that we use. This is a bijective function, so that we can also return it if you know the key, so that we can reproduce the original plain text from the cipher. This is approach number 1. We learned also about 2 chiffres. So first is the Caesar chiffre, which is shifting all letters by a specific number. Maybe here key is 2. Being able to, so if you have numbers, then you can also have a number 0. That would be to keep the letters at the same position. But here we have key number 2. Then we shift it by 2 letters. And if we have letters, then we don't have a 0. So an A would be equal to 0 and B would be equal to 1. That's a Vigenère chiffre. And there we have a keyword. And the keyword baby would relate to this kind of pattern. So -2 would equal to, I think, plus 24. And if we apply it to Bingen, then we first apply the 4 letters of the key to the first 4 letters. So B is shifted by 1 to C, I is shifted by 0 to it remains I, and so on. So you see how from Bing applying the key pattern 1 0 1 -2, it results in C Y O E, and then we apply for the next 4 letters, but here we have just 2 letters. Again the key baby, and here we apply just the first 2, so basically 1 and 0, and EN becomes FN. So these 2 as an example of the permutation. Then another key function that we typically have in symmetric encryption is to apply some kind of substitution, where we have some kind of substitution table. In this case, this is from I think DES. It has some information which substitution table to select. We just ignore it for a moment, and basically you have, let's just take this kind of row, and here's the input, and it tells you which substitution you have to make. So for example 0 0 0 becomes, okay, in this case it's still 0 0 0, but let's say 1 1 1 becomes 1 0 0, and 1 0 1 0 becomes 1 1 0 0. So you see the number of the occurrences of zeros and ones change in contrast maybe to the permutation. If in the permutation you had previously, let's say 2 ones and 2 zeros, then with a permutation you could change the order, but you still had 2 ones and 2 zeros. And with a substitution you can also change that. And of course using the key, so by knowing which substitution table to select, and you have this as a cipher, you can identify what the input was, and you can return to the previous plain text. And the third element that we had in the symmetric keys, in symmetric encryption, is XOR. This is quite simple. If you have a plain text, here M, and you have a key, you just compute the XOR from that, and you get a cipher text. And the nice element is that, again, you get the cipher from XORing the plain text and the key, and if you have the cipher and the key, you can get the plain text back again. So basically all of these functions are reversible in the case that you have the key. And what the symmetric encryption basically does is to apply various combinations of these 3 functions over and over again in let's say 16 rounds, let's say 64 rounds, and you get a very difficult cipher text as an output, in the sense that only by using the key and having the key you can really reverse it. Otherwise, there are so many combinations what could have been the plain text that it's infeasible to try out all of these combinations in reasonable time to find out what could be a meaningful plain text. So, and then we had a look that one of the core challenges in symmetric encryption is the question, how do we exchange the key? This is, I mean, to have on both sides the same key is essential in symmetric encryption. So how do we get this key? And one of the, obviously we cannot just transfer it, because once we have the key, we can communicate securely. Once we do not have the key, we did not yet exchange the key, we don't have the opportunity for that. So we need some other option. And one option we learned is about the Diffie-Hellman key exchange, where basically the main idea is that you have a number. So you have a finite set of elements, of p many elements. So this p is a prime, basically with numbers from 0 to p minus 1. And G is a so-called generator that by iterating over all possible numbers or exponents of G, you basically get this whole set. So it has to be, it must not share any kind of divider with P. Okay, and the trick is now A selects some kind of secret for herself, Bob selects a secret, A communicates which P and G she's using, and this is the trick, her A is G to the power of A, and B applies the same and communicates G to the power of B, and this information is all can be overheard, can be obtained by by the attacker, but from A and B you cannot generate the key, so this is not possible, but by either A and B you can generate K, or by B and A you can generate the key by basically both apply the same. So G to the power of B to the power of A equals G to the power of B times A, and the same here, G to the power of A to the power of B equals G to the power of A and B, and because this is a simple multiplication, it is also exchangeable. So this is a simple mechanism to exchange a key, and this is very I mean that we will see in the later real protocols that this is a very core mechanism that is used very frequently. Okay, and then we finally arrived at the point where we started to discuss public key cryptography with the radical idea that previously we had one shared secret key. Yeah, that was the core element, that both receiver and sender had the same key. They used a little bit different algorithms afterwards, one to encrypt, one to decrypt, basically to reverse the encryption. But in public key cryptography we have two different kind of keys that are really fundamentally different. Everybody can have the public key, and the private key is only known to the receiver, and this is also identifying the receiver in one point. So it will be able to encrypt for everybody because their public keys are public. So everybody can use the encryption key, but not decrypt it later on. Just the person who has the private key, the corresponding private key, can decrypt the encrypted messages to them. Okay, so let's have a look at what the core mechanisms are, and then we will dig with these basics into all the various security network protocols. So, how is it applied? So again, the public key is more generally used to encrypt information for somebody, but it is not limited to encryption, but in most cases it is used to encrypt. Basically you have an encryption algorithm, the message comes in, ciphertext goes out, and you need the decryption key to get the plain text out again. And basically, in contrast to the symmetric approach where you had the shared secret, you never knew, I mean, it was possible to hand over that secret key to somebody else, and you didn't really know whom you are communicating to. But in this pattern with the private key, what you could do is to really verify that somebody has this private key and only that person has that private key. And then you can also provide some kind of authentication because that only single person is able to decrypt the message. Okay, so this is really some quite novel idea. I mean, this is and mathematically also not too complicated. So it's really very interesting how it works. So look at how the core elements are. So basically, again, we have these two functions that cancel each other out. Yeah. So basically, if you apply the two functions after another, then you get the same what was the input. And interestingly, it will also be that the order doesn't make any difference. So if you first apply the private key and then the public key, you get the same. So they really cancel each other out mathematically, and they are not bound by their order, in which order they are executed. This will be a very nice property. So, and yeah, what constraints? I mean, everybody can have the public key, and once you have the public key, the private key should be impossible to compute the private key out of. Impossible in that sense that it is always mathematically possible, but it takes a very, very long time. So, and that long time should be so long that it's not reasonably justified. So it might take millions of years. Okay, and let's have a look at one of the prominent ones, and especially those who introduced it by Rivers, Shermier, and Adelson, the RSA algorithm. And we have there some kind of yeah, let's see how this builds up, what requirements we have. First, we look at this mod operator, and the mod operators, what's the remainder of x when divided by n. Typically, by this you define a set of numbers that can only be in this range. So the remainder in this division is only between 0 and n minus 1. And the common rules of mathematics apply. You still have this how's it called? What is this? What's the rule that you can, if you have a that you can basically apply? So if you have a mod n plus b mod n, you can put that together. So it's not commutative. I think that's where you can exchange the order. Distributive, yeah, that's a distributive rule, distributive law in regular arithmetics. So it's very similar to a times c plus b times c equals a plus b times c. So the order, so you can apply this kind of distributive law. Yeah. The same also applies for minus, and the same also applies for multiplication. So very convenient. And what we also have is the same. So if it applies for multiplication, then also if you have the exponent, this is just a sequence of multiplications, then it also applies. Just as an example, so to get the feeling. So if you have, for example, 14, x equals 14, n equals 10, and d equals 2, and we write this term, and then it's 4 to the power of 2, mod 10 is 6. But we can also take in, I mean, these are exchangeable. So we could first apply the mod, or we could first apply the to the power of d. So that would also apply, but it just allows you to take shortcuts in the computation, because you can identify which operation is more convenient or more efficient for you to compute, and then do the computation in that order as you wish. Okay, so let's see how, after this prerequisite, how RSA is working. So the message is just a bit pattern, so any kind of message that we have. So we have here hello. This is then transferred to, I don't know what, that's 8, so that should be 87 as an ASCII character. I think it starts with 80 or, and the ASCII character A. Which bit does it equal to? I don't know. and so on. So it's just a set of bits, so it translates to some kind of bit. I don't know. So you have at the end just some kind of number. So you have a very big number that you can, that you basically take as an input. So doesn't matter what your message is. And at the end, it will be a finite amount of bits that relates to some kind of number. And this single number is then used in the operation. So we just encrypt one single number at the end. I hope this is somehow can be related. Yeah. So if this is our, let's say, what would be that? This is our message. So yeah, 8 bits. This would be number 145. And again, if you have a very long text, yeah, so lorem ipsum, then what is typically done is you chunk it in specific sizes so that it fits to your given basically number limitation that you have in your algorithm, and then you apply that first to the first block and then to the second block. And this would be some approach how you can split up a very long data stream in smaller bits that you can actually process. So, and then we encrypt M, and then we get corresponding, we get the new number. So basically the cipher is also a number. That is what we send in relation as a ciphertext. Okay, so let's go through it, how this operates. So let's take, how do we create a public and private key pair? So let's, as an example, take two very large prime numbers. So it's essential that these are prime numbers. And first we compute two numbers. Oh, this should be also red. So this should be also red Z. Admittedly, I mean, this I think in IT security we have the same approach. I think there we called it phi of n. It's called Z here, and at the end it's just variable names. So you have two numbers, so n equals p times q, and z equals p minus 1 times q minus 1. So and now, this was step number 1. So typically this is a very classical exam question where you have p and q given and you should compute the other elements. So let's choose e with e smaller as n, because in our numbers, so we will operate at the end, we will operate mod n. That means that our numbers that we have must be between 0 and n minus 1. So we take e as an element of this, yeah, of this set, and it should have no common factors with z, so this set. So they are relatively prime. So if e has the factors, I don't know, 5, 7, and 3, then z should have other prime factors except 3, 5, and 7. Okay. This is simple to do because you just have to identify any kind of number that lies in this set without having the same factors. The more difficult part is to select d in a way that the product of e times d minus 1 is exactly divisible by z. So that, yeah, so this is equivalent e mean minus 1 minus k times z equals 0, or it's equivalent to ed minus 1 equals any kind of factor times z. This is also equivalent to e mod z equals 1. These are all equivalent statements. Okay, and then basically we will use as a public key a set of two numbers. So n must be given and e must be given. Typically e is also quite standardized. So sometimes it's even set that e should be, I don't know, 655,536 or so. I don't know, or 5. So some kind of random, standardized number. And so this is quite public. But n is the specific one that typically differentiates between the various public keys of different people, and e is often equal, so that you will find sometimes. And n and d is very different to everyone, so this is a private key, and it's what we will do is basically to take e and compute. So once you have e, you can compute d out of it using n and z. But otherwise, the other direction from d to e should not be possible. Okay, so let's see. That's a simple element. So we have n, z, e, and d, and that we have. And how do we operate with this? So let's say we have the two keys. So this is the public key. This is the private key. And then we just take m to the exponent of e mod n. Again, we are in the same number space, a finite space of 0 to n minus 1, so n should be quite large, that we get lots of numbers in. That's our ciphertext. And if we apply c to the power of d, then we get our plain text again. Because once we have this, basically, what was our c? So this was c, yeah. And what we get out of here is m to the power of ed mod n. And as you see, that ed should cancel out to 1. Let's have a look. Yeah. So somehow by magic, this should happen. Mod n. So mod n. And this is the one kind of, actually that was the invention, how they combine these findings. Let's have a quick look how this works. So when we have basically this kind of pattern, so we want to decrypt, therefore we need the ciphertext. So the ciphertext to the power of d should be m, where this is the ciphertext. So actually we have m equals m to the power of, let's put in what was c. C was m to the power of e mod n. This was c mod n. And that, to the power of d. And that means m to the power of e times d mod n. So, and this should somehow be 1. And there's some kind of, here it's written as fact, and that has been proven. There's some papers on it. There's some very, very long proof for that. It's basically showing that if you have two numbers x and y, with the property that x to the power of y is, they have this characteristic. So basically you can, so if you have that mod n, and mod n is a product of two numbers, and and you compute z with this property, then you can apply the mod z to the exponent. I mean, obviously, so there's a very long proof for that. I don't go into detail, but this is the trick, that basically you can squeeze in the mod z here if n has this kind of properties. So, and the trick for RSA is especially that that n is selected in this specific way, that z is selected in this specific way, and e and d are selected in this specific way, that mod z, their product, equals to 1. So this was the exact setup that was required by RSA, using this kind of mathematical property, where we don't show you the proof here, but yeah, maybe I will put it online, but you will see this is just for the very interested reader, let's say. So and with this setup, this property holds. I mean, this holds, and e and d cancel out. And what you also see, that also this is equally the same, because this is simple multiplication, where you have the commutative law, and you can exchange the order of the products, of the factors. So by this, if we enter it and we have selected C and D, if we have selected E and D and N and Z based on these properties, then we see that our setup, our idea really comes to place. So let's see. So this is our C. Our C is this. This is how we build it. This is C. So there's just standing C to the power of D mod n. Then here we can apply that to the power of E and to the power of D, and both are mod n. We can basically create m to the power of ed. And now we have this rule coming in, that we can compute mod z for this exponent. And because E and D have been selected in a way to be, here what we apply is E and D have been selected with the property that is equal 1. It equals 1. So this was the property, and Z has exactly the property equals P minus 1 and Q minus 1 with N equals P times Q. That was how Z was selected. So basically we all heavily selected our variable requirements based on to meet this criteria, and because we have selected it, so we have this property, and it equals to 1 in the exponent, and by m to the power of 1, that's still m. So this is the core idea, and let's play it through at one example, let's say. Let's have here an example. Okay. So let's say Bob chooses P equals Q, and P equals 5 and Q equals 7. So this is N equals, so this is P times Q. So, and this equals P minus 1 times Q minus 1. Okay. So that's obviously 5 times 7 and 4 times 6. So you see how this relates. Okay, and then we have to select E relative prime to Z. So what are the prime factors? So this is 24, and the prime factors are 2 times 2 times 2 times 3. So basically just 2 and 3 are prime factors. And we have to select E to not have the factors of 2 and 3. So this is, for example, 5. Okay, so and now we have to find a number where it is E times D should be, one moment, should be one more than any kind of, so it should be E times mod Z equals 1. That means that E times D minus any kind of multitude of Z equals 1, and that means E times D is just one more than a multiplicand of, so some multitude of Z. I think this is it somehow visible and clear? Okay, so we have to select 5, and what I recommend, so is to have a look. So 5 would be one option in this case, because 5 times 5 is 25, and this is one more. So I mean, this is one more than Z. That would be an option for D, but it's probably not the best choice to take the public key equal to the decryption key, to the private key. So we look further on, and basically what you can do is, just let's see. So what are the multitudes of Z? So can we have some kind of 25 that we saw that we can have? So it's basically 24 plus 1 that we can have. It's 42 plus 1, 48 plus 1. That's 49 that we cannot reach by a multitude of 5. Then it's 72 plus 1. It's also not a multitude of 1. So this would be, okay. Then we have 96 plus 1, also not. And then we have, what's the next? 120? 120 plus 1. Am I doing it right? Yeah, I think so. And the next one is 144 plus 1. This is 145. And this is equal to E times D, 5 times 29 equals, how much? 1, 2, 3, 4, 5, 6. 6 times Z plus 1. So this is our D and this is our E. So you have to find any kind of multiplication where you meet a multitude of Z. How to write it? Multitude of Z, but you should be one larger. So by this, we have found our D. As I said, we could have also selected D equals 5, but this is a bad choice. And now we have identified our D, and this applies. So we have an input, let's say 7 bits. No, it's 8 bits with 1 there. Strange, is it? Strange 1. So equaling to, a little bit confused what kind of bit pattern equals in this 12. Why shouldn't there also be a 1? One moment. Let's make it this way. Okay, now I don't have keys. Okay, so let's, I think that here should be also 1. And this is a 1. And then we have 12. Then we have 12 and m to the power of e mod. Okay, this would be 12 to the power of 5. And in order to get c, we have to take it mod n. That's mod 35. Can do it quickly. Let's have a look at, is the calculator capable of doing that? And I mean the right calculator, not the wrong one. So let's have a quick look. So it's 12 to the power of 5. Hmm. 12 to the power of 5. Why is there 1 8 more? Okay, it's very okay. Obviously, there's some. That's strange. That's very strange. So do I have here some mod operator? Mod 35 17. So at least partially it's correct, but I have to correct that on the fly. Otherwise, it's one moment. I think I know why. Okay. So now it's correct. Okay. And now if you want to decrypt it, it's 17 to the power of 29. Yeah. So this should be 17 to the power of 29. And this is this nice number. I'm not really sure whether this is will also be computed. So 17 to the power of 29. Oh yeah, it's the same number. I see it from the pixels. So and if you take that mod 35, then we get 12 again. So it's somehow working. This is nice. Of course, if there's some similar example in the exam or so, this will be not the numbers that you will have to face. Okay. So So keep in mind, for this process, basically we have this property that we require that it works, that n and z are selected in this way in order to allow to take in the exponent mod z. And because we want to use that property, what we did is to compute especially e with the property that it has no common, that it's relative prime to z, so that they don't have any common factors. And we selected d with that property that e times d mod z equals 1. So that was the strong properties that we required for RSA for creation of the keys, because we want to use that kind of mathematical element in order to cancel out the exponent in the decryption. Okay, and what we also see is that the order doesn't really matter. So it doesn't matter whether we first encrypt our plaintext message and then decrypt, or first apply the decryption and then apply the encryption, because in the first place it will be m to the power of it's encryption first and then decryption equals m to the power of ed, and here we have it will be first decrypted and then encrypted equals m to the power of de, and you can exchange, you can swap the order of the multiplication and the exponent, so this is equally the same. Okay, yeah, I see. I have it on the next slide as well. So it's basically that you can replace the order because it's a simple multiplication. And the nice thing is that we will also see this is used commonly in order, especially that what does this statement tell us? This statement might be something like I am Bob, or let's make it different. So the message could be I am Bob, and somehow this is encrypted with the private key. So, and now everybody having the public key can decrypt this message. That means everybody can verify, yes, the message I am Bob has been created with the private key of Bob, because somehow we will know that the public key is related to this private key. So we can also use it to have some kind of signature element. Okay, why is it secure? What is the difficulty in this? The difficulty is basically because it's why is it hard to determine D? So if everybody would be able to have D, then it would be of course of no value. And the question is, can we and basically we not only have D, but we also know that one part, of the private key, this N, is also public. So we know N is public, E is public, and the question is, can we somehow derive from these two numbers D? And the question will be, so it would be possible, because what did we do? We had N equals P times Q. If you have P and Q separate, then you can compute Z equals P minus 1 and Q minus 1. And if you have E, that was also selected to be relative prime to Z and public. So if you also have E, that we also use in our computation, then what we did is derive D. So what is difficult? So this is something that the attacker has. This is only possible if P and Q would be public, would be somehow known. P and Q are basically starting points for the one who creates the keys. So this is what the key creator has. And this is what the attacker has. So basically the attacker has these two information. It just has N, let's say. But what is difficult is this step. So basically let's make it this way. So what is difficult is if you have N, difficult to get the factors it is made of. So if that would be possible, then everybody else could follow up the procedure, calculate P and Q, calculate Z, compute D. But this single step is difficult, so basically factoring a big number is hard. And as long as this is given, it is not possible to get out of n, which is public, the two main factors P and Q. And being hard means it takes a very long time, and the long time being maybe in millions of years. Okay, so what can we do with this? So it solves two problems. Problem number one is the key distribution, and and second, it is allows to encrypt and decrypt. So why do we at all need some kind of symmetric encryption? Why do we talk about this? If it's so outdated, has some difficulty, it doesn't have a proper key distribution scheme. And with this public key, it's very simple to announce to everybody a public key and everybody could communicate. So the problem is that this is slow. So what is typically done is that RSA is used in a way to, so basically it's written exponentiation and RSA is computationally expensive, so the whole approach is slow. And other symmetric encryption schemes are much faster, because what do? Permutation, substitution, table, and XOR, and these are very simple things to do. It's just bit operations, but this exponentiation is very difficult, especially with very large numbers. So what is typically done, and that we will see, I want to basically showcase that there's a common pattern with very many security protocols that we will later face, where you first establish your key and maybe some authentication, then you establish a that you have first somehow identified whom you are communicating to, then you establish a first secure connection using public key cryptography. But you use it only for exchanging very few information, basically just symmetric session keys. This is how the key exchange problem is used for the symmetric encryption. So basically you have first the public key encryption. You encrypt the session key that you exchange, and then you have symmetric encryption using this public key, and all the data is exchanged with the symmetric key. Maybe later you will have a session key number 2, 1 1, and then you encrypt the data with, so this is K1 encrypted, this is K2 encrypted. So you see the slow encryption mechanisms are only used to encrypt the session keys, and the data is quickly and efficiently encrypted. And this combination of public private, so basically asymmetric encryption used to exchange a symmetric key and then to use symmetric encryption, is also called hybrid encryption, because you use both of them. I think on one of the slides it will also be placed, but this might be the right place to showcase how this is used. So, and once the session keys are exchanged, then they use just a symmetric encryption to exchange their data, and then and when it can be renewed based on the secure channel they have with the public key encryption. They can send each other messages. It's a little bit slow, but it's for small data only, so the keys are not that huge. Okay. Last element for the properties of this of both. So what did we up to now face? So if we have the regular, I think we had the security goals. Typical security goals are, first you need some kind of authentication, that you know whom you are talking to. Then you want to have some confidentiality, and you want to have some integrity. Okay, So basically up to now we've discussed a lot of confidentiality issues. So how do you encrypt messages from A to B? This is what we covered now. Then we will cover now a little bit of authentication, what kind of options we have there to identify whom you're actually talking to. Because up to now, also in this hybrid approach, we did not have any verification whose public key we are using and whom we are communicating to. And also for the session keys, we had Diffie-Hellman key exchange approach, but whom did you exchange the messages with? You exchange with somebody a key, that's fine, but you don't know with whom. You have no verification. So let's have a look what options we have for verification of the identity. That's basically authentication. Verification of identity. Yeah, that's I am Bob. Somebody's claiming to be someone, and you need some verification of that. Yes, and then will come the integrity element. Okay, let's see how can we go through this? What options do we have? So, what verification options do we have? The very simplest one is to say I'm Alice. This is just the identification. So if anyone tells you I'm XY, what can go wrong? Obviously, people could be lying, and that's not sufficient to just have the identity claim. So let's see something else. I mean, so they cannot see each other. So here's basically some kind of network. There's just a message in which stands I'm Alice. What further information do we have? Maybe we know something, a message is coming and it has some source IP. It has the destination IP of Bob. Obviously, otherwise it would not arrive at Bob. So it has also some kind of destination IP, which doesn't help us to identify Alice. Somebody claims I'm Alice and sends the, let's say, even correct IP address. And the message is coming with a header in which it stands, it comes from Alice and it's sent to Bob. What can go wrong? The same thing. So it's an IP address is like a letter where it has some kind of sender information. So the sender is Alice, yeah, and destination is Bob. And anybody can write any kind of sender information on that letter and throw it in the box, post box. You don't have a verification that it's really coming from Bob, from Alice. I think even, I mean, I'm not really sure whether this is true, but sometimes in the past it might have been possible that you write a letter and you write as a sender the person that you want to send the message to, and as a recipient, I don't know, some other random address with too low stamp page, so that you have too less stamps on it, and then the message will be delivered back to the sender, which is the person you actually addressed. So you can fake your address that you send messages from. I'm not sure whether this is true. Don't try it. Okay, it's just an analogy for IP addresses. Okay, so this is also not sufficient. What else can we do? So let's say both have some kind of agreement on some kind of password they have, and you have a letter. I mean, where you write on the letter, again, same scenario. A sender is Alice. My password is XY, and the message should go to Bob. And now there's some kind of confirmation coming back from Bob. And obviously, as the same letter example, everybody can read this message, can record what's written on it. The message is passed on through several steps. And if somebody copies that information, Alice and password X, then everybody could send in the name of Alice some messages. So also not sufficient. So we need something else. And what else can we do? So this is a typical playback attack where you just record a message and play it in later on from a different source, maybe. Okay, you can also encrypt the password. So let's say again you have the message coming from Alice. Now we have it encrypted, so X is not anymore, but it's Y. And Bob accepts everything that has the correct encrypted password. So also in this case, this is basically the same. It's just the password has been somehow modified, but everybody can record it as well. It's also not sufficient. So let's see what kind of elements we can apply. Okay, what they could also do, sometimes banks did this, and what they have is that they use some kind of nonce, meaning a number used only once in a lifetime. So this is a number used only once. I don't know. I mean, I don't know. So number used once. Okay. So let's say I'm Alice, and now it's the source IP address is from Alice actually, and now there's some kind of nonce coming back. So it's really verified that the message is still arriving at Alice. So it cannot now fake basically the recipient by, this is a so-called handshake, because it's not a one direction communication, but it goes back and forth. And the idea is that everybody can claim they have the source. Yeah. Again, the post example, if you say this is from Alice address, to Bob, and Bob sends you a letter back to this address, then it will arrive at Alice's place, so it's not at Trudy's. So this is already one kind of improvement. And let's say we put a nonce there, some number that has not been used previously and will not be used in the future. It's just a random number. And now they have some kind of shared secret, let's say, where it is verified that the person that Bob is communicating with has the secret key of A and B. So what can go wrong? Any ideas? Have you really verified that this is Alice that you are communicating with? Well, I mean, yeah. So if we use keys, so others, and I mean, let's say that the two persons who have this common key, they agreed on some key, but let's name it just the key K. And does it tell us that the key we have exchanged with is from Alice? That's basically the core question. Or did I get your point? Did I not get your point?
It's not the specific key of Alice, although
yes.
key only Alice can have. So the problem is really gets the key she can verify it as well, and then we finish everything.
Exactly. So we don't have the confirmation that the key has been previously exchanged with Alice, because we are currently in the authentication step, and here it's somehow assumed that we already have that information about Alice. So it could be also some key that we exchange with somebody else. So what could happen is one moment. What could happen here is let's make it. So let's say this is Alice, and Alice sends out an information. Alice, I'm Alice, and it arrives at Bob, and Bob sends back the number used one, also a random number. And Alice then confirms with her key A, B. Okay, and Bob is happy. But of course, what could happen is that Trudy sits in between, and she follows on and says, I am Alice. And Bob tells Trudy the nonce, and let's make it this way. A moment. And Trudy just forwards on the nonce that she got to Alice, and Alice responds with some key that she actually exchanged with Trudy, and Trudy forwards on the message that she actually exchanged with Bob. And now Bob received from somebody who he thought is Alice and who he had a key exchange with. In this case it was Trudy and Bob key, and Alice was communicating with Bob, to whom she exchanged some key with, and the key is actually A to Trudy. So we didn't really verify whether there's some man in the middle trying to intercept our messages, because what happens now, Bob believes that the message is coming from Alice because it used the key that was exchanged with Alice as he thinks, and any kind of message that is sent now is passed to Trudy. Trudy can verify it, can read it, and pass it on encrypted to Bob. So we still have this man in the middle, and we did not verify whether the person Alice is really bound to this key. So this is the big question. How do we know that the specific person is bound to the key? So let's see how public key, so this is with symmetric keys. We have the flaw of how do we verify that the exchange key is really with the person that we talk to. And here in the next step, the next element is with asymmetric key. I mean, previously we had the problem, it required that key, and we need to assume that it was the correct key. And if we use public key cryptography, then we can say I'm Alice, and we can confirm that we have the private key corresponding to Alice. And in that order, it's a little bit, okay, it's a little bit, does it work in this order? So let's say we have this, Alice confirms this is the key and send me a public key, and now I send a public key. And then we can compute, okay, it's really the person has confirmed that that they have the corresponding private key. Does it, any flaws that you see in this? Can Trudy claim to be Alice? Yes?
I think it's basically the same problem, because if Bob wants to get the verified message and ask them for the public key, we ask someone else for the signed message and the public key, so Trudy can send her own public key as well, and so man in the middle is possible.
Exactly, yes. So there's no information about anything about Alice here. So these are just two numbers, and it's actually just one single number. So there's nowhere Alice written, and that could be as well Trudy. So Trudy can, so if this would be Trudy, or Charlie, or Dave, or whoever, so just introduce some further people, then they could still make false claims. So let's say, how can we bind the name Alice to a specific public key, let's say, yeah. How could we, what is the approach to do this? Because this is a core question that we have, that somebody verifies us that this link is really actually true. And therefore we need some extra steps. Okay, so yeah, Trudy is still, so this man in the middle is still working, yes, as you see. I mean, that's what we talked about now. So let's have a look. Okay, so you don't have any kind of verification whom you communicated to, and Trudy can act as Alice towards Bob and act as Bob towards Alice. So both might think that they're communicating to the right person, but actually in the middle there's Trudy converting and reading all messages. Okay, so let's see, how can we bind exactly that so that Bob is linked very strongly to the public key of Bob. And as a first step, what we have to do is Okay, some further elements on. Yeah, let's still jump to it, and then I will jump back. No, I cannot. No, I first have to do this. Is it right? Is it right? Yeah. Okay. First. Okay. Okay. Some further elements on the signatures, because we need that in order to see what we can do. Is it right? Yeah. Okay. Yeah. 2 more slides on signatures. Okay. So still assume. Let's assume we would have this feature. Let's assume we know that Bob is linked. I don't know how to write it. Linked to this public key. To the public key, because this is public. This can be public, and both confirmation can be public. So all of this is public. The name, the public key, and the confirmation that they are linked. So let's assume we have this link. Then we can use following the property of being able to exchange basically the key. We can exchange the order in which we apply our encryption or decryption, or basically the cryptographic function. So this would be, as we said, m to the power of d to the power of e, and this is m to the power of e, because we first apply the public key and then d. And there we can exchange that. So this is very practical, because let's assume we have this property. We can just hand out signed documents. That would be a document that everybody can get. So it's basically a message encrypted with the private key of Bob, and everybody can have. And everybody can verify that by using the public key of Bob, assuming this detail, that really Bob created this message. And this is quite practical. So because that would really be identical to verifying that the document owner and creator is Bob. And this really acts as a signature. So it's verifiable. How is it verifiable? You just apply the public key of Bob to it, and it cannot be forged because you somehow assume that only Bob has the private key. Of course, Bob could hand out his private key, but then it would become worthless. So if somebody, let's say you have a copy of your signature as a PDF stamp, and you hand it out to other people so that they can also create documents with your signature on PDFs, or somebody can replicate your signature, then your specific signature would be worthless because it cannot refer back to you. So it's in Bob's interest to keep that private key private. That's why non-forgeable. It cannot also be recreated without the consent of Bob, and it's verifiable because everybody using the public key can check. So everybody, as Alice, can prove to someone that Bob really and no one else, not even including Alice, must have signed a document. This is a very nice property, including Alice, because if you compare it to the symmetric key that is shared between Alice and Bob, in the symmetric encryption, both could have created document any kind using the shared key. So, and then let's say if there's some document, Bob wants to give Alice a lot of money, and you have used some kind of symmetric key to confirm this, then both could have created that document. But using this private key to sign a message in this way, where Bob claims I want to give Alice lots of money, then only the owner of the private key, being Bob, could have created this document. So how it's created? You just apply the private key, and you can have a message. You put in your private key. You encrypt with your private key. So at this point, encryption and decryption is basically the same. It's just the question which key you apply. If you apply the public key in putting it into exponent, then it's an encryption. If you put the private key, then it's a decryption. Or, I mean, it's still the same mechanism where you have M and you put in the public or private key or whatever. It's basically this D or E that creates the output. Okay, so and how does the signature look like? So first you need the message that you send, and then comes your signature. Why is that? Because this message, I mean, it should be readable what you write. So it should be somehow readable. Let's make it that way. And this signature is then can be verified with the public key. So if you apply the public key, then on this signature, then you get the message out of it again. So, do you see some drawback? Do you see some drawback in sending this kind of information beside that it is public? We're just now at the point of confirming authentication. So, who created the document on this document? One more practical drawback could be seen here, and just assume that M is a very large message. It's a very long blah 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 message. So let's say these are 4 megabytes love letter. How large is then the signature? Yes? Exactly, this is the same size. So this will be something that is not so really optimal. But okay, so let's say this has been sent. Now we receive this message. So we receive the message with the signature. I mean, we receive the message and then the signature. And now Alice can verify by applying the public key to that message. And then, because it will result in, this is M to the power of D mod N. This will result in M to the power of D to the power of E mod N. This will result in, sorry. So N equals M to the power of D E mod N equals M to the power of 1 equals M. So it's confirmed that. So why do we need then actually to send M? So couldn't we just leave that out? So why do we need this? Okay, this is for the signature, but why do we need this? Because now we can compare basically whether the output M equals to this output. Otherwise, if bits are changed, then maybe there might be a difference visible. So let's assume we have now verified that really this outcome shows us that it has been really, because we used the public key of Bob on Alice's side, and something came out that is related to what we should compare it to. We must deduce and conclude that the private key has been used in the creation of Bob, and because it's still assumed that we know that this public key belongs to Bob, and we see that the corresponding private key has been used, so we know Bob has created the message. Whoever assigned M must have used Bob's private key. Okay. So basically we need, so it's working. That's the first message. So assuming 2 elements, element number 1, we have the confirmation that Bob is somehow linked to the public key of Bob. Okay, this is assumption number 1. And one problem that we want to face next is if this is 4 megabytes large, then this is also 4 megabytes large. Why is that? Because if you have a very long number, so this M is a very large number, in the range of 0. Okay, do I have the space? So why are these very large numbers? That's the, okay, that's, okay, so yes, this is verified, assuming that this holds, and its non-repudiation is also confirmed. That means that Bob cannot deny to have created the message. So, why are the messages large? So the messages are large if, as we know, let's say this is your long text, this is the love letter 4 megabytes. But we have the issue that M must be not euro, but should be element of 0 to the power 0 to n minus 1. Is it right? So maybe if we take this as a whole number, this is too big. So therefore we might chop it into pieces. Yeah, let's make that this. Now each piece is between a number between 0 to n minus 1. So if we apply k to the Bob and M1 let's say, and then we get as an output still a number of this size, still in the realm of 0 to n minus 1. And the same also applies here. So the message still has the same size, because you take a large number of, I don't know how many bits, 1024 bits, and you recompute it mod n, it will still take 1024 bits. And for the whole data stream, if you had 10 chunks before, then you have 10 chunks afterwards. You don't compress anything. So the problem is that the signature in using just the private key is as exactly as the input it confirms. And instead of just sending the message once, you basically send it, you require always twice the size. So this is not optimal. 4 megabytes here might be a small issue, but if you have gigabytes, terabytes, then it will be a problem. So we need some kind of placeholder that still keeps the same properties. And here, as a next step, what comes into are these message digests, or so-called hashes. And this will be a placeholder that is keeping the same properties. So the motivation that long messages are the result for signatures. If we want to just verify that a message is confirmed as we wanted in the previous element, the signature, then we don't, then it's sufficient to have some large, this might be large, but it's okay if it's just some small signature, yeah, as long as it assigns the nature of it. So basically that it cannot, that it's somehow linked to that message. So what we have is to have some kind of fingerprint, some placeholder that is just of much smaller size, easily to compute, and a fixed length. So even if you have 2 terabytes of data, you get, let's say, 160 bits as a fingerprint, and that is not placeholder, it's a representation, sorry. That's representation or fingerprint, so it really should be something that represents, that summarizes the content of the big data that is the input. So, and therefore we use the so-called hash functions, cryptographic hash functions, and the output, so the input is again a bit array of indefinite size. So it can be, I don't know, 1 byte, it can be 2 terabytes. So it doesn't make any difference. So the input size is, if we take sigma being, so it should be sigma star, so basically a combination of zeros and ones. A combination, so if this is our alphabet, that would be zeros and ones, and an indeterminate number of selections from that alphabet, zeros and ones. So it can be 8, it can be 7, it can be 2 million, no matter what. And the output should be of fixed size. That means that we still have, let's say, an alphabet, but let's say 160 characters from it. So 0, 1s and 160 only. Whether you had 1 bit as an input or whether you had trillions of bits as an input. So it always maps to the same size. Because this property, obviously, the first set is much larger than the second set. So here you have only 2 to the power of 160, and this is 2 to the power of whatever. So it can be 2 to the power of 2 trillion. It doesn't matter which size you take. And obviously, because the map set is smaller, so you will have various points. If you take a single one, then you have various points pointing to the same. So it's a many-to-one property. It produces a fixed size message digest. But the point is, if you have a point here, so this direction, mapping it to the function, that's easy. But if you have another point, let's say, so it should be hard to identify from what was the original value that was used to map to that specific element in the target set. So it's computation. If you have a digest, so this from this hash set, it should be computationally infeasible to find an M such that x equals the hash of M. That's the property that we want. We'll also talk about how we can achieve this, but let's say we have this kind of function, and especially this is the core quality of it, that it has a fixed length. That's basically simple to achieve, but the core element is that it's infeasible to compute it back. So basically the only option you will have is to iterate over all possible M's and to find whether it by random matches to the X, your digest. So if we have this element, this characteristic function, then we can do the following. So we have a large message. This is M. It's 2 terabytes big. Then we take a hash function of it. This is just 160 bits, let's say, or 256. Then we only apply Bob's private key to the hash. How large is the outcome? Roughly 160 bit. Then this 160 bit is also transferred. And basically what we send out to Bob is a 2 terabyte M message and 160 bit hash. So as you see, obviously, previously we had to send 2 terabytes for the message, 2 terabytes for the signature, and now this signature is just negligible, so it's really so small that we don't really care about the impact on the overhead it has. And now Alice receives the information, so it takes basically the message and the signed hash of the message. It takes the message, it creates, so this is M, it creates the hash function, and it gets a number, so 160 bits. Let's say this would be hash. And then it takes the signed hash, it decrypts using Bob's public key, that's public, and it gets another hash, H dash, and then it can check is it the same, and if yes, then she knows, okay, the person who sent me this must be the owner of the private key of Bob. So I assume this is Bob, because we still have to make the conclusion Bob private is linked to his public key. Somebody needs to verify that really this happens. And then we see, okay, by using Bob's public key, and this is really linked to Bob through this property. So this is Bob, because so we know this is linked to Bob, and that means that Bob has the corresponding private key. So if somebody used Bob's private key, then it was Bob, and then we can verify, okay, this hash has been really created by Bob. And if the hash matches to the hash of the large message, then we know, okay, really Bob has sent me this message, because Bob used his private key to create the hash, to create the signature for the hash, and I've verified that the hashes match. Okay, so it's a very nice property, and now we have all building blocks together. Basically, okay, maybe just one step. What kind of hashes are currently available? So there's MD5 has been used. It used 128 bits. There's a 4-step process. We'll have a look how this is basically created. So it takes there SHA-1, there's SHA-2, and I think now in more discussion is SHA-3, 160 bits. So how can you create a hash? So just to give you an idea of how you could create a hash, it's basically you need two properties. Property number 1 is you get an arbitrary input, and it produces a fixed sized output. And once you have hash from m of m, you cannot create m. So it should be computationally infeasible. And one similar property we already had. So basically, if you have a key, let's say symmetric encryption, and you apply it to some message, then you have something encrypted, obviously. But without having the key, if you don't have the key, you cannot get m. So what the idea for creating such a hash function would be is to take the message and encrypt it somehow with a key derived, how to do it. So somehow you derive from the message the key. And then it results in some kind of cipher, and without having the message, you cannot, this is not possible to get m without having m. This is the core element, and basically that's still very easy to do. So basically you just need to have some kind of mapping from this large set of numbers. So let's say again you have this stream of data. This is your big M. You split it in parts. You apply, what can you apply? So you take one part and you apply it with XOR to the other part. You can use permutation. You can apply some substitution table. So it's various similar elements that is used for symmetric encryption, that you accumulate the bits and use basically one part of the bit as a key for the next part, and you take as a whole and use as a key for the next part, and basically you have this kind of property where you apply the message on itself, and that's then the hash of the message of the fixed size. And without having the message up front, you cannot calculate it back. That's the core idea how a hash function could be created. So now we have the building blocks of symmetric encryption. We have the building blocks of public asymmetric encryption, and we have this digest, so this hash function. And now let's see how we can apply all our characteristics. So we had already confidentiality by the encryption. Now we want to achieve authentication. So how can we do this now? So let's say if Alice claims she's Alice, isn't it the same that we still had? It is the same. So we, I think the point was here that we still need to have the element that Bob is somehow linked to his public key. If that would be, let's assume that we would have this property. If we would have this property, then Trudy would not be able, then we would not need this step, send me your public key, because there might be a repository with all the names, and for Alice it is confirmed that this is Alice's public key. Then we would be able to reject at this point. So if we would have, again, this repository, so let's say we assume there's a repository, Alice is linked to this, and Bob is linked to that. Then it's very simple. Alice sends a message to Bob. So let's encrypt it with Bob. And we can also say, I don't know, please. I don't know. Yeah, let's take the hash of the message, and that. Sorry, it's a little bit confusing. So, okay, let's encrypt with Bob. Then we send a message, and we sign with Alice the hash of the message. So, Bob receives the message. Bob looks up, oh, I got some, maybe there's also written, yeah, that's maybe also, I don't know, I'm Alice. Okay. So now Bob receives the message. Bob can look up from this repository that in fact Alice has this specific key. Bob can then check this and retrieve the hash of the message. Bob can anyway use his private key to encrypt this one. I mean, he gets the whole message. So what he gets is M and Alice, that we already used Alice information, and then Bob can use to compute H of M here and compare it to this one. And now we have basically seen, okay, because here in this process really this information that is corresponding to M has been encrypted with the private key of Alice, and we know Alice is using this private key. Then we know that the message is coming from Alice, and another. So we have on the one side we have the authentication, yeah, because we see that really the private key of Alice has been used. We have confidentiality, because the public key of Bob has been used. So it's in this point. Yeah, so here conf. Here it's authentication. And we have also integrity, meaning that the message has not been altered. Integrity. Because we see if any bit in this M would have been changed, so this would be M star, then we would get a different hash as an outcome. So basically, by comparing the hash that Alice sent with what we received, you can verify whether bits have changed during the transmission. And if the bits have not changed, then basically that's meaning integrity. Nobody has changed the content without being observed or being detected. Okay. Yeah, actually, then we would be through. Actually, but we have, I don't know, I don't like to really overtake it. 1 or 2 minutes. I still. So just to quickly 1 minute, what do you want to confirm? So one step was still standing out, that the public key of Bob is belonging to Bob. And there we have this public key certificate, public key infrastructure. Basically we have companies, that's company, certification authority, there you go by foot or somehow, and you verify I'm Bob, this is my public key. And then they ask you, okay, if this is your public key, then please sign this random number. Okay, this is the random number signed. And then the company can verify applying the public key that you said to your signature and verify, yes, it's really the random number that you said. So you are the owner of the private key. And then they create a document in which it states this is Bob, this is his public number, a public key. We are following issuer, company XY. The validity of the period is this and that. I don't know, 2007, 27/01/01. and it needs a signature of the company, the certification authority. That's the core elements of a signature, and basically that you can show everyone, look, this company, certification authority, confirmed, they checked my identity, and they checked I have really this public key, and they wrote this certificate. It can be also put on repositories, everybody can download, and next time Alice wants to communicate with Bob, yeah, she just gets Bob's certificate from the repository or from Bob, and she believes that certificate is really a good company, and they checked it thoroughly. And how do you trust the certificate authority? It's basically hard-coded in your operating system and in your browser. There are a set of providers that Firefox and Chrome and Microsoft and Google and Apple and so on trust that they are good companies, and those certificates, their public keys are hard-coded basically in your devices that you must match. And here's an example for certificates. It's written this person, so it's Graffi in this case, this is the issuer, this is the validity, these names are still valid for the public key, this is the RSA information that is used, and this is the public key. Yeah, and here's the certificate. Is it right, the signature? No, it's not. It's the signature algorithm, and the signature is still there. So this is basically the key elements, and that's what I wanted to wrap up with, just to show you how you have this. So if you go to about, I think it's certificates, this is the authorities that are by nature trusted. So basically the operating system and the Firefox are trusting these people, these companies, that they do a proper job. For example, there's, I don't know, it's DigiCert, Global Root, GE, and they have self-signed their certificate, so the subject they confirm has the public key. Here's the public key. This belongs to this person because this person says it. So, okay, that's so far it. Next time we will really dig into the protocols. Thanks for keeping up for 3 minutes with me, and see you then next time.